For the next session, Odyssey Network in Action, I would like to introduce you Professor Cohen Kim from Department of Thoracic and Cardiovascular Surgery, Seoul National University Hospital. He's a president of Heart Valve Disease Forum Society and also a vice president of the Korean Society of Medical Information. He will lead keynote session as a chair. Let's give him a big round of applause.
예, 여러분 안녕하십니까? 예, good morning, ladies and gentlemen. This session, the OHDSI Network in Action, first speaker, Pat Ryan, is a senior director and head of epidemiology, analytics, Janssen Research and Development, and also an assistant professor of Department of Biomedical Informatics at Columbia University Medical Center. He is an original collaborator in OHDSI, a multi-stakeholder interdisciplinary collaborative to create open source solutions that bring out the value of observational health data through large-scale analytics. Today he will talk about OHDSI Community in Action. Ladies and gentlemen, please welcome Dr. Pat Ryan. Yeah?
Thank you very much. It is a distinct honor to be here at the OHDSI Korea Symposium. I want to thank the organizing committee and all of the leadership. Professor Park, thank you for all of your work. I want to congratulate everybody on their contribution to the Book of OHDSI. It is a very impressive accomplishment that you all have had to make this available. I see that the first chapter is still listed as written by George Ribsack and myself, and I have to say that I'd never thought I could write Korean so well. So, but congratulations, it's a distinct honor to be here. What I'd like to talk about is the power of community. And to a certain extent, I think that I may be preaching to the choir because you all are impressive leaders in our community in what you are doing by working together. But I hope to provide some motivation for the work that I think that we can be doing together as a community, and to hopefully encourage more of you to be thinking community first as we do work together. We are all on a journey from taking data in trying to generate evidence that can improve the health of patients around the world. There's lots of different types of evidence that we could generate. We can generate clinical characterization evidence to understand diseases and treatment patterns. We can use this data to support understanding of clinical research, and we will talk about that later this afternoon. We can use this data to generate evidence about population-level effect estimation, studying the causal effects of medical interventions. And Martijn and Chen will be talking about work in there. And we can be using this evidence to generate patient-level prediction models to help patients understand what treatments are best for them and to try to intercept disease as possible. But if we're going to talk about being on a journey to generate evidence, it's important for us to first define what makes evidence reliable. And we've been thinking a lot in the OHDSI community about what is reliable evidence. And we've identified 6 attributes that we think are necessary for evidence to be considered reliable. Let's see. The first is repeatability. It should be the case that if evidence is reliable, that a researcher who has a question, who has access to the data, and who applies methods to the data should be guaranteed to get an identical answer over and over again. But research needs to be reproducible. It needs to be the case that a different researcher can take the exact same data and apply the exact same methods to get the exact same answer. The only way we can achieve reproducibility is if we are fully transparent in the process that we follow from the journey from data to evidence. This is something that could be done by a given individual or maybe a partnership between two individuals. But for evidence to be reliable, we also need it to be replicable. That is, the same research question answered by different researchers using the exact same methods on similar data should yield similar results. And this is important for the OHDSI Korea because it is unlikely that any one hospital in Korea is sufficient to answer any question that we have. But if we start to learn answers across the Korean network, then that might be evidence that's reliable for the Korean population. But more generally, we're also interested in evidence being generalizable. That is, the same research question could be asked not just in similar data, but in different data around the world, and we could see whether or not we achieve similar answers. So it is interesting to think about how you all, as a community of data within Korea, whether the findings in Korea apply to other parts of Asia or other parts of the world, and similarly, whether findings from the other parts of the world can come here to Korea and inform clinical practice in your country. Now, for that to be the case, we also want evidence to be robust. That is, that research questions answered using different methods produce similar answers. And we'd like our evidence to be calibrated. That is, we can trust the statistics that we produce. And Martijn's going to talk a little bit about that. But the one thing that these elements have in common is that no one individual, no one organization could achieve these attributes of reliable evidence. We need a community effort that works together to figure out what are the important questions that need answering, that works together to establish data standards that we can all agree to, that works together to develop open source analysis tools that can be applied to generate evidence in a transparent and consistent way, that works together to establish best practices for how to generate evidence, and that works together to disseminate that evidence to the right people who can use it to inform medical decision making. We need a community approach to generate evidence in a reliable way. Now, it turns out that this is challenging because we're not just one community. We are actually bringing together many different communities to conduct observational health data science. There's the community of clinical experts, those who have direct knowledge of disease and treatments and the management of patients. And this knowledge is absolutely essential to doing this work. There's the community of data, people with data expertise who really understand the data source and its structure and content and understand the issues associated with the data that will come into the analysis. And then we have a separate community of researchers who are focused on methods, who have hands-on knowledge of how to apply epidemiologic designs and statistical methods to data to generate reliable answers. And it's the intersection of these three different communities that allows us to try to generate evidence that we think is reliable. Now, this is a challenge because very few of us live in that intersection between those three answers. So just a show of hands, how many of you in the room right now feel as if you are part of the community because you contribute clinical knowledge? That is, you understand populations or drugs or outcomes. Please raise your hand if you have clinical knowledge that you're bringing to the community. Probably about, it looks like maybe about a quarter of you feel like you are contributing clinical knowledge. And how many of you here feel like you are contributing data access and understanding the data capture process, the care setting in the health system itself? Raise your hand if your contribution is data understanding. Okay, so I'm seeing about 20, maybe 20% or so. How many of you feel like your contribution is methodologic expertise? That is, you are bringing epidemiologic thinking, statistical programming, or informatics integration to the table? Please raise your hand if you are methodologic expertise. Okay, so maybe like another 15% or so. And how many of you feel like your contribution is in evidence synthesis? That is the clinical interpretation in the review of the evidence and the dissemination of that knowledge. Raise your hand if evidence synthesis is your contribution. Okay, some hands. Now, if you noticed in the room, if I asked the question, who has all of these prerequisites? Who has the competency for every single piece of this? I don't think there was hardly anybody, inclusive of Christian, that really could attest to being an expert in all of these areas. And I think this really underscores the point that if we think these are all necessary to generate reliable evidence, and none of us have all of these skills, then all of us need to work as a community to collaborate together to achieve our shared goals. Now in OHDSI, we like to use the analogy of what's happened in the domain of physics, in particle physics. For many, many decades, researchers in universities and industry was conducting physics at a certain level and realizing that the big problems in physics couldn't be solved by working by themselves, but they needed a totally new way of doing research. And so they collaboratively developed the Large Hadron Collider at CERN. And they came up with a new way of doing research. Instead of each and every researcher doing their own research by themselves, they decided that the best way to do research was to work as a team together and to celebrate their collective achievements as a community rather than competing with each other to generate evidence. Martijn introduced this idea a couple years ago that maybe what we are doing in OHDSI is we are trying to build the Large Hadron Collider for observational data science. So what I'd like to take the last 5 minutes of my presentation is to talk about how well we're doing towards this goal. And to do that, I want to first start by reinforcing the ICMJE guidelines for authorship. Raise your hand if one of the things you would like to achieve is to publish scientific findings in clinical journals. Raise your hand if that's of interest to you. Not very many hands got up, about half of the hands, okay. Well, if you would like to be an author, the recommendations for guidelines suggest that being an author requires you to do 4 things. To make substantial contributions to the conception or design of the work, the acquisition, analysis, or interpretation of the data, and that you should draft the work or revise it critically, and that you have final approval of the work that's published, and that you agree to be accountable for the integrity of the science that you've conducted. This is what it takes to be an author. Now, in OHDSI, we started, and Dr. Ripsack published an early paper in MedInfo, and in that one of our first papers we published, we introduced the idea of collaborative research for observational data science. And you can actually see in this paper, Professor Park was right there at the start when we were trying to bring this to the community. Now what I'll highlight about this is that this was a paper that had 17 authors, and it had one promise, that we were going to find a way to do open science community collaboration in a different way, and that this was going to be the start of a journey to try to bring everybody together to collaborate as a community. So how are we doing? Well, George mentioned this paper that was published in the Proceedings of the National Academy of Science, focused on clinical characterization of treatment pathways. What I'll highlight is that this paper had 17 different authors, including Professor Park, and 11 different databases from around the world. And our key insight that we gained was that you learn a lot more by having a worldwide data network than you could ever learn by having only one data source by yourself. We published a study in epilepsy that focused on a safety question associated with a particular drug. This was a network study of population-level effect estimation. It had 13 authors, and it summarized 10 data sources to generate evidence. Later in the OHDSI community, we published a paper that looked at comparative effectiveness of diabetes treatments. And in this work, that included multiple authors from from Korea, we actually had 22 authors and 8 different data sources represented here. Now, at last year's OHDSI Symposium, we conducted a research study live in the meeting. A meeting just like this. We started the day by asking what's an important research question to answer, and at the end of the day, we delivered the evidence. And that can only be done through collaboration. And indeed, a team of researchers went through the steps of doing patient-level prediction, and at the end of the day, stood up together and presented those results. This work has actually resulted in a paper that was just accepted for publication last week in PLOS One. And as a community effort, this included 23 authors and 11 different data sources to examine whether or not we could predict hemorrhagic transformation. Peter mentioned the Oxford Studyathon, and indeed we brought a community together for a week to study how well we could, what we could learn about knee replacements. And in that 1 week, we were able to design and execute a study that has now been published in Lancet Rheumatology. This paper has 26 authors looking at 5 different databases and examining the comparative safety and effectiveness of different treatments. The Book of OHDSI, which we are all quite proud of, we are proud of it because of what it represents in terms of scientific content. But one of the things I'm quite proud of is the fact that we have a very large list of contributors who made meaningful contributions to this book. 56 people contributed to the original Book of OHDSI, and now that community is growing with your Korean translation. So why do we need more collaboration? Well, first is we want to learn from as many data sources there are around the world. To generate reliable evidence, we need to be able to replicate findings, look at the generalizability of findings, and examine the heterogeneity of effects. But that means we need partners to contribute with their data. Turns out that as the number of data sources grows, that means it's likely that the size of each data source will get smaller as we find more and more niches of data. And what you're going to hear from Chan and Martijn is the introduction of METIS as an effort to examine this methodologic problem that we're now facing. But it's also important to see that large-scale evidence generation requires large-scale collaboration. George mentioned that in the Lancet study, we've now published 1 paper in Lancet, but there are many other hypotheses. And what we've had to do is establish a collaboration where different researchers tackle different hypotheses to inform. Chan is leading a question about the comparative effectiveness of beta blockers, which is relevant because the Korean guidelines for hypertension suggest something different than the American guidelines for hypertension. So one study around the world could have different implications in different countries. So we're trying to build the Large Hadron Collider for observational data science. And the question is, if we had thousands of collaborators around the world, what are we going to do with them? What are we going to do with you all who are going to participate with us in research that requires thousands of researchers? Because the Large Hadron Collider, this community that's been established, they are publishing a paper every single week of new scientific findings. A new paper every week. And when they publish their papers, just like this most recent one, they list out the 1,000 authors of their paper that their findings represented the collective achievement of. And here's another one of their papers where they had 2,900 authors on their research. So what research question are we going to answer that requires the collaboration of 1,000 researchers across the OHDSI community? Well, I will posit some big opportunities we have to improve the lives of patients. In methods research, I think we could imagine a paper called Examining Data Heterogeneity Across a Global Data Network. And that'll only happen if we bring together the world's data. We also need to invent new methods that integrate causal inference and machine learning to examine patient-level estimation. On the open source development front, imagine a paper called The Implementation of a Large Science Analytics Ecosystem to Enable Evidence Generation Within Health Systems and Across a Global Health Network. You all have established software that is running within the Korean network. Some of that has been showcased at local OHDSI meetings, but none of it is actually being used around the world yet. But we have an opportunity as a community to build one platform that works not just for Korea, not just for any one organization, but works for the entire world. And that's something that would get a paper that would have 1,000 of us on the co-author list. For clinical applications, I think there's an opportunity for us to use the global network to characterize disease incidence and treatment utilization patterns around the world. And this is something that would get mainstream attention if we could work together on that. And just as George showed a comprehensive comparative safety and effectiveness of hypertension treatments, we should be doing legend studies for every disease that matters for patients. And the only way we're going to be able to do that is if it's not just 5 or 10 or 20 of us, but if thousands of us band together and collaborate to generate the evidence necessary to improve the health of the world. So I want to invite and encourage all of you that as you are joining this journey and you are bringing your data to a network, I want you to think about how you can make a contribution to a broader effort and to tackle some of the big problems that are facing healthcare and hopefully come together so that we can work on those problems as one community. So with that, I'll stop and turn it over to Martijn, who will introduce how we can think about best practices for generating evidence at scale.
Thank you. Next speaker,
All right.
Martijn Schuemie. Let me briefly introduce him. Martijn is a senior director at Janssen Research and Development and co-leading the development and definition of best practices for observational research. He is working on methods for estimating average effect sizes in observational calibration of effect size estimates and patient-level prediction, as well as supporting the conversion of databases at the CDM. He is also a creator of the White Rabbit and Rabbit in a Hat tools and is contributing to the OHDSI methods library. Please.
Thank you. Thank you for the introduction. So it's an honor to be here at this OHDSI Korean Symposium. Thank you, Professor Park, for inviting me here. So today I would like to talk about best practices for observational studies. And why do we need best practices? Well, the reason is we strongly believe, I assume, in the power of observational research. But outside of this room, there are many who are not as excited about it as we may be. So for example, a year ago this paper was published where the authors, as you can read from the title, claim association is not causation. Treatment effects cannot be estimated from observational data in heart failure. And so what they did in this paper was to look at findings from observational research and compare them to findings from randomized trials and to see whether there was agreement. And well, we all believe that randomized trials are somewhat of a gold standard, somewhat. But they found that there was actually very little agreement and that observational research tended to find very, very inconsistent findings. And actually George also showed some examples of internal inconsistency in observational research. And so what is the problem with observational research, and why did these authors also believe that it's actually not very reliable? Well, they point to what they call residual study bias. or confounding. So if you have a randomized trial, because of the randomization, you can simply observe the effect of the treatment, the drug, on the outcome directly, and the randomization should basically make the groups comparable enough so that you can directly observe that relationship. But in a non-randomized study, an observational study, there's a problem that people that get one treatment tend to be different from people that get the other treatment, and this can lead to confounding. And some of this confounding is known, and we adjust for that, but other confounding might be unknown or might not be recorded in the variable that's doing the confounding might not be recorded in the data. And so even after adjustment, there will be residual bias in observational studies. So these authors pointed to this as the primary problem why observational research tends to be not so reliable. But I think there's another problem, and George briefly touched on this. It's shown in this graph. So what we're showing in this graph is every dot represents an estimate as was extracted from PubMed from an observational study. So on the x-axis is the hazard ratio or the odds ratio or whatever effect size they were estimate they were using, and on the y-axis is the standard error, so how wide the confidence interval is. And so every dot is just from a PubMed abstract, the hazard ratio with its confidence interval or the odds ratio with its p-value, it's represented here. And so you see here almost 60,000 of these estimates, basically the output of observational research so far in published literature. And so even though this plot is showing all sorts of observational studies on very different outcomes, very different treatments, using very different designs, I think you agree with me that there is a pattern to see here. And the pattern is a little bit made clearer by that red dashed line, which is the line where you reach statistical significance, where p equals 0.05. Anything below the red dashed line is statistically significant. And I think the pattern here is very obvious that there is a very suspicious cutoff at 0.05, p is 0.05. The reason why we see this is because of publication bias, and you probably all heard of that. So if you want to publish a paper that has a non-statistically significant finding, that's actually very hard to do. And so sometimes researchers don't even bother to try and publish this. It just disappears somewhere in a drawer, the research, and it never gets shown. The problem with that is that publication bias doesn't just hide things from view, but because of the multiple testing that's going on, that's hidden, what you end up with is the things that do appear in published literature tend to have a very high false positive rate. And so the mathematics of that is a bit complex, but basically that means that if you do see something in literature that's statistically significant, there is a very high probability that actually there is no effect. What you also see in this plot, but a little bit harder to see, is p-hacking, which is a different process, which basically means if you do a study on observational data and you find your result is not statistically significant, quite often you see researchers then say, oh, I must have done something wrong. They go back to the design of their study and they change it, and they keep on doing that until they reach statistical significance. And this is a process called p-hacking, which also leads to false positives. So in summary here, I think there is a real big problem with observational research in that if you look at individual studies, they are often biased due to confounding, selection bias, and measurement error. And if you look across the field, observational research as a whole is even more biased due to publication bias and p-hacking. So we actually have a real problem that we need to address if people are going to take observational research seriously outside of this room. So how do we achieve reliable evidence? And Patrick already explained some of the key characteristics of what reliable means, but how do we actually get there? So we highlighted three core aspects. First, you need to pre-specify what you're going to study. I think it's a very obvious thing to do, but many of us don't actually take the trouble to do this. So you need to pre-specify before you do the study what question you're going to answer and how you're going to answer it. And then you need to commit yourself to that path. Run your analysis only once, don't go be hacking and go back to your analysis. You need to be transparent. So others should be able to reproduce what you do. As Patrick already told you, the ability to reproduce a finding across multiple data sites, for example, is very important in increasing the reliability of evidence. And last but not least, and I think this is so the first two ones everybody in the world agrees with. This last one is more of an odyssey point. You need to validate your analysis. So that means that not only should you declare that this is how you're going to answer your question, and just basically assume that people believe that that is the right way to answer the question, you should actually have empirical evidence that the way that you're going to answer the question is the right way to answer the question, and also that what your analysis does is actually exactly what you said it would do. So I'm going to use the Legend hypertension study as an example of these three principles. So Legend stands for Large-Scale Evidence Generation and Evaluation Across a Network of Databases. And George already told you quite a lot about this study, so I can be brief there. So one of the papers that came out of Legend is the one shown here. So let's go to that first principle, pre-specify. So also, George already explained this in much more detail, so I'm going to be brief about this. We predefined a very large set of research questions, almost 700,000 research questions comparing all first-line hypertension treatments, both monotherapy and combo therapy, and we looked at 55 outcomes of interest, including safety and effectiveness outcomes. We added 1.6 million control questions, so questions where we already know the answer and we can see whether or not we get the answer that we know to be the truth. And we applied a standardized advanced causal effect estimation procedure, which I'll go into detail later on. So the method that we used is to address confounding is instead of hand-picking a few covariates that we believe should be adjusted for, we have this generic approach where we create a large set of covariates, somewhere between 10,000 and 100,000 covariates that are generic to the question. So independent of what our exposures or outcomes are, we always use the same set of covariates, and this includes all drugs that were previously taken, all conditions that were recorded for the patients, etc. Everything that occurs at baseline. We use a regularized regression to fit our propensity model, and then we match or stratify in the propensity score. And one of the strengths of this is that even though we have this large set of covariates, this procedure actually achieves balance on all of them. And so we often are criticized that we didn't think about confounding, which is a kind of a joke, because we thought about confounding a lot. And we can actually show that no matter what variable you can think of, we're balancing on it because we're balancing basically on anything that we observe in the data. And so this process is described in this paper that we published a little bit over a year ago. So transparency, so others should be able to reproduce your study in every detail. So in Legend, we wrote a protocol, of course, which is the recommended practice. And we published this, or we made this available beforehand, before we actually executed the study. But not only that, in Odyssey, we believe that a protocol is nice, and it's a human-readable description of the questions you're going to answer and how you're going to answer them. But human language tends to be a little bit ambiguous, no matter how hard you try. And we believe at the same time that you publish your protocol, you should also publish your study package. So this is actually a machine-readable description of what you're going to do. So this is basically the actual analytic code that executes the study described in the protocol. And so both of these were made available before execution of the study on our GitHub site, as shown at the bottom. So this is what I just said. Yep. All right, so last, validation of your analysis. So this actually is a very involved subject, which we call evidence quality. And it breaks down into 4 further components. Data quality. Are the data of sufficient quality for your research purposes? clinical validity. To what extent does the analysis conducted match clinical intention? And this is mostly about, do the outcomes of interest, for example, capture the actual clinical outcomes that we're interested in, or are they perhaps by error capturing something slightly different than we think they do? Software validity, does the software do what it is expected to do? This is not a non-trivial question. And lastly, method validity, is a method valid for answering the question? So I could talk for hours on all four of these topics. I'm not going to do that. Fortunately, I don't have the time. But I do refer you to the now Korean Book of Odyssey, very cool, where there's actually a chapter on each of these components for you to read. I just want to briefly touch on method validity, because that's one I'm very interested in myself, and talk about the process we use for measuring residual bias. And so for that, what we do is we think of a study as an instrument that is intended to measure something. And so it's actually very much like a scale, where the scale is, you measure the weight of something. And you want to prove that that instrument is accurate. You don't just want to assume it, which unfortunately a lot of people in the field do. You want to prove this. And, well, how do you prove this? Well, a scale, if you want to prove that the scale is accurate, what you do is you simply take objects where you know how heavy they are, and you put them on the scale, and you see whether or not the scale actually gives the right answer. In observational research, we should do the same thing, and so that's why in Odyssey we promote the use of control questions. And so we have two types of control questions. One is a negative control, and the others are positive controls. And so these are exposure outcome pairs where we know what the effect size is. And so George already gave an example of ingrown nails, I think, where it's an example of a negative control where we know that the hazard ratio should be equal to 1. And now we can run our analysis method on the data and see whether it actually, for the ingrown nails, finds a hazard ratio of 1. Because it's very hard to think about just one negative control, what we actually tend to do is use a lot of them. So we typically use somewhere between 50 and 100 negative controls, and then we use some math to analyze that. But the key part is to use these controls, run your method with the data on them, and see whether they produce the results that you expect. And just like on a scale, if you find that your scale is a little bit off, there's usually a little knob that you can twist to make sure that it then becomes calibrated. So we've developed procedures that can use these results from the negative and positive controls to calibrate your method to make sure it actually produces a reliable estimate. And so this is one of the papers published in PNAS that describes this process. So George already briefly showed this, so this is the output of the LEGEND study. So these are all the 1.3 million estimates coming out of the meta-analysis across all of the databases. If you compare that to literature, that looks very different. Importantly, in our LEGEND results, we do not hide anything on small effects, because for a doctor, that's probably just as important to know as a big effect. The study bias, so the confounding primarily, is addressed through these negative and positive controls, and of course through our advanced method for dealing with confounding. And there's no p-hacking and no publication bias, because we've disseminated all of this, so you can just go to our website and get any of these dots as a result and analyze it further. All right, so that was my part just on best practices. I also briefly want to talk about a new project that we're now working on together called METIS. And that's specifically for doing research in a distributed research network. So not everybody has a research-free zone that Professor Park just announced this morning, which is very exciting to see happen. A lot of the times in Odyssey, we have to do research in a distributed fashion. And what it means is that in Odyssey, we have many sites. For example, hospital electronic health records. We have administrative claims data. And each of those sites have converted their data to the OMAP Common Data Model. but they're not allowed to share patient-level data. That means if we want to do a study, well, that's still possible, but then one of these sites will need to take the lead in that study, and any site in OHDSI can become a study lead. I think that's a very nice democratic aspect of OHDSI. And then that site will develop analytic code that will answer the question that they're interested in, and send that code to each of these sites. The sites then run the code against their data locally, so nothing is shared, and they produce results. For example, a hazard ratio with a confidence interval. And then it's only these results that get sent back to the central site, and then maybe synthesized to produce a single effect size estimate. And these results that are sent back, they're not patient-level data, they're aggregate data, so there's no concern there about patient privacy, for example. So that's a very neat idea, and people like that a lot, especially in Europe because of our concerns over patient privacy. And it works really well, but it has some issues that we're now discovering that we actually need to address. And so that's actually the goal of the METIS project. Two challenges that we've observed is, first of all, that if you have a distributed research network where there are some smaller sites, and small is a relative term, some of these sites actually do not have enough data to fit a propensity model, which you usually need quite a lot of data for. So Seng Cheng will tell a little bit about that in his talk. But another problem we've observed is that the normality assumption is not met in the outcome model. And I just want to briefly tell you a little bit about what that actually means. So imagine that you have in your distributed research network one site that produces a hazard ratio of 1.02 with a confidence interval as stated there. What that means is that usually there is an assumption of a normality, a normal distribution. So really, if you look at the underlying statistics, we have a likelihood distribution on the hazard ratio. And so there's the optimum at 1.02, so that's the thing that we communicate. But other values are actually also have a non-zero probability. Actually, this whole blue area is the area where 95% of the probability of this effect size is, and the boundaries of that's our 95% confidence interval. And so that's what we tend to communicate from a single site. This works well if you have very large numbers, but it actually doesn't work that way when you have small numbers. And by small numbers, let me just show you this particular site. We had 22,000 people on the target treatment. And I don't actually know what the treatment is, but it's irrelevant for this example. And 130,000 people on the comparative treatment. So we had 150,000 people in this site. So that's actually what I would refer to as small numbers, but that's huge, of course, for many sites. Because what is small is the number of people that experience the outcome while on the drug. So we had 3 people experience the drug while on the target and 25 while on the comparator. And in that case, this neat distribution that I just showed actually isn't normally distributed anymore. It's slightly off. So here the dashed line still shows the normal distribution, but now the blue line, solid line, actually shows the actual distribution. So it's a slightly skewed. The confidence interval is actually slightly different from the one that your normal Cox regression in R would give you. And so you say, oh, this is a minor problem, of course, but this is just one site. Now here's that same site. I don't remember actually which one of it is, but now this is 4 sites on the same question, and they're all basically have a low counts, just hundreds of thousands of people. And then if we assume normality for all of them, we get a hazard ratio estimate using meta-analysis of 1.74, and it's actually just barely statistically significant. But in fact, if we were to not assume that they're normally distributed, we get slightly different results for each of these sites, and these actually add up. And so now we see if we drop this assumption, if we were to actually be able to share data across sites on patients, then we would be able to compute a hazard ratio that has a confidence interval that very comfortably includes 1. And so just this normality assumption that we all take for granted just led us to conclude that there was a statistically significant effect even though there was none. And this problem actually, what I just showed you was a benign one where all of the sites were still able to compute a hazard ratio and a confidence interval, but this is an example of even smaller counts where we had 2,800 people in the target group, 15,000 in the comparator group, so 17,000 or 18,000 patients in all, small, but nobody had the outcome in the target group. And so normally, so there's the likelihood distribution, there is no optimum and there's no confidence interval, so normally we would completely ignore this site in our distributed research network because we have no way of communicating this information. So we just ran the analysis on 17,000 people and now we're going to throw away that information. And so what is the solution? Well, I think I said to Patrick, I think the solution is trivial, and then Patrick said, well, this is not a trivial solution, it's just an elegant solution, but we should just not communicate just the hazard ratio and the confidence interval, we should just communicate that entire shape. Basically just, you can have the image file for all I care and just send that over. So each site computes that shape and they just send that to the local site and then we can combine that. And so we ran some initial results on that. So again, using these 4 databases that I showed earlier. So the top row is showing what would happen if we were able to pool the data, which in this case, because it's a test environment, we were able to do that. And then below that, just below that, is the traditional meta-analysis. So what would happen if we would just use the approach that we're currently using? And you see that it's not a huge difference, but like the first example is showing that we reach statistical significance, even though there isn't. The second example is showing that we get a wider confidence interval because we had to throw away sites with 0 counts. And the third example is showing a combination of the two. And then I'm showing 2 approaches that we've been evaluating. One, the grid is really, like I said, just basically transmitting the image, so just the x and y coordinates of that shape. And the custom function is trying to be a little bit more clever and trying to just summarize the shape with a couple of numbers. And you see that both of those approaches in this case just basically get you the same answer as if you were able to pool the data, but without actually pooling the data. So just having this normality assumption in a distributed research network adds unnecessary bias. The problem that I showed might be small, but as you add more and more databases, 10, 20 databases in your network, this can get to be a really serious problem. If we just communicate the full shape of the likelihood function, we can completely avoid this problem. And we're now running some simulations to explore this, but most importantly, in the METIS project, we're looking forward to actually evaluating this at very large scale in the OHDSI, Korean OHDSI network, and to show that this is a helpful contribution. And with that, I'd like to thank you for your attention.
Thank you. So our final speaker, Dr. Yoo-Seung Chan, is a medical doctor majored in internal medicine. Currently, he is a PhD candidate in Department of Biomedical Informatics, Ajo University. He has joined OHDSI community since 2016, started research within this network, and received the Best Community Contribution Award for Clinical Evidence Generation and 2017 OHDSI Symposium. And 2018, he released a clinically informing package based on RNN. It is an open source software for predicting clinical outcome in OHDSI tools using deep learning. Currently, he works for integrated clinical data with radiologic, genomic, environmental, and free text data based on CDN. So today he will talk about OHDSI Korea in action as a community. Please.
Thank you for a kind introduction. I'm too honored to be here. So I'd like to speak about the we are, the Korea is the digital country. So this flag, you can see the binaries. So everything is in binary. So this flag actually shows that great harmony between yin and yang. And 2 bars means yin and 1 bar means yang, which is 0 and 1. And this red means yang and blue means yin, which is 1 and 0 too. Okay, so this flag is really digitalized, and we are the digital country, I think. And I'd like to tell you about the Koreanicity in action as a community. So Lao Tzu, the greatest philosopher in the history, said that we need to learn the virtue of water because the highest good is like water, because water excels in benefiting the myriad creatures without contending with them and settle where none would like to be, which is underneath, and it comes down to the ocean. Odyssey means a long journey full of adventure. And if you see the 6th objective, Odyssey, innovation, reproducibility, openness, community, collaboration, beneficence, you can feel the virtue of water here. So it is truly collaborative international community for open science and reproducible research. And I'd like to address this kind of these topics, and I skipped the vocabulary thing because others will tell about this. So as we mentioned, that we translated the book of Odyssey into Korean. Actually, Ilsan Hospital released the guidebook for OMAPCDM and EDLAS before for the Odyssey Korean community in March 2019. This book actually have the more than 200 pages, and it was really great contribution to our community. And after that, after the publication of the Book of Odyssey in the United States, we started to translate this book, and we did first translation during 2 weeks. So I started this project on the 7th October, and we finished the first translation on 18 October. So it takes 2 weeks. So these are our contributors of the book. So I'd like to say in Korean of them. 강미라 교수님, 김도 선생님, 김미나 선생님, 김희석 교수님, 김청 선생님, 박내영 교수님, 박유진 선생님, 박지명 선생님, 박철환 선생님, 신서정 선생님, 양영보 선생님, 오성희 선생님, 유정 선생님, 윤사정 선생님, 이상경 선생님, 이상원 선생님, 이일정 선생님, 임지영 교수님, 장정현 교수님, 장진성 선생님, 전명 선생님, 전학교 선생님, 조재영 선생님, 차원철 교수님, 박수 한번 부탁드립니다. 네, 다. So you know that no single penny belongs to them when selling by this book. So all the money will be donated to the COSME, which is a Korean AMIA. So they will not, get money from this. And you can see that we committed a lot. So more than 500 commits, and these 2 people actually contribute a lot, my boss and Sang-Kyung Lee. And currently, I closed the online book now. So I closed the GitHub and I closed the online PDF version of this book because by the contract, I can open that online book again after selling more than 1,000 books. So please donate to the open source spirit. You can think like, oh, if 1,000 people can buy it, then after that I can just access to the online book freely. But I don't believe that you will think like this. You can think like this, but I don't believe you will. So please donate to the open source spirit. Next, I want to just briefly speak about the themes in Korea. So we do have the Themes Korea working group here. So, and we are sharing the issues or ideas about the ETL in Korea. So if you have any questions or if you have any issues for ETL thing or about CDM, then please write your questions here and we'll solve it together. And I'd like to say about the Odyssey Dathon in Korea. So as my boss said, we do have many activities in Korea about OHDSI and many tutorials, but I'd like to focus on the datathon in Korea. So we did have OHDSI datathon in Korea in October 2019. You can see how you can feel the atmosphere at there. So it was really vibrant. I was really happy with them and to work with them. So another cardinal principle in OHDSI is that all actionable packages are alike, but every adult-generated non-actionable OHDSI package has errors in each one way. So our goal is to build actionable package as a study pipeline and presenting the results and uploading the package to the GitHub and release it. We prepared 5 replica CDM database on 3 different database servers. We prepared with 10G network system, and we prepared another dedicated server for RStudio based on Docker images and with monitoring system with Portainer and Elk stack. And we conducted stress test 3 times. So 10 students clicked the generate button and the Atlas and executed our packages simultaneously, and we want to make sure that it works. And we prepared questionnaires as a survey before and after the datathon. So actually, we developed 10 actionable packages within 2 days. Actually, it was 1 day. And we released it with the full protocols and the ideas or objectives of those studies. And this is the result from the survey. So the perception about the CDM was actually changed after this datathon, and you can see that the participants believe that their performance about the CDM was improved after this datathon, statistically significant, And their perceived importance and performance was improved after datathon too. So you can see many people believe that their performance was improved after this datathon about data understanding, analytics, and or tool understanding. And finally, I'd like to talk about a METIS project. OHDSI is the ocean of observational healthcare data across the world. So OHDSI is composed of myriad of small to big healthcare data across the world. So you can see many rivers come to the ocean. Every database joins OHDSI after a long journey, just like the way a river joins the sea. But we do have the challenges. So in this distributed research network, we suggest that to use large-scale purpose score matching for population-level estimation, which is we just match over 1,000 of variables. And it is hardly possible for data partners with small to medium-sized database to participate in OHDSI network studies because they usually cannot fit accurate propensity model. So if you conduct studies, you've seen plots like this. It means that you don't have the good balance after propensity matching, and it bothers us. So method, the Greek word metis meant quality divine wisdom and cunning, and Odysseus was the symbol of this metis in the Greek myth. And in the Greek myth, Metis is one of the Oceanids, which Oceanids are the daughters of the Oceanus and Thetis. This implies a circulation or some sort of water. The river is mother of sea, not the sea is the mother of father of the river. But because water is circulated, so you can it makes sense. So Metis is one of the river in this myth. And Metis is the first wife of Zeus and the mother of Athena. Zeus actually literally shallowed her and took her wisdom. So she provided wisdom and deep thought to Zeus inside him. This is the ancient way for transfer learning. So actually, this is truly transfer learning. So Metis is just shallowed by him. So to overcome current challenges, so we make several ideas to overcome this current challenges. So we thought about the transfer propensity model, which learned from the big database to the small database. So apply the propensity score model generated in the big database just on the small database. And this is the experimental results. So I conducted 2 identical studies on the 2 different databases, which one has very many people and the other one is very small people. So you can see that in the big database, the target and comparator patients were more than 400 million, still that 400,000, but in the small database, we do have only about 200 people. And you can see that in this big database, we can feed propensity score model very appropriately well, but in the small database, our propensity score model was not that good. Actually, it's nothing. It's hardly have any information for its propensity, because we batched more than 50,000 covariates. So actually, I transferred this the propensity models which generated in the big database on the small database. So the maximum difference of the balance was a little bit decreased from 0.747 to the 0.4, a little bit, but the results is still disappointing. But still, we do have other projects like that, more better, improved ideas. So we're thinking about the transferring propensity score model from the big database into small database, and improve within small database again by using Bayesian updates. Or we can just circulate these propensity models around the small database, around them using Bayesian updates. So Mark Sussard is working on apply this Bayesian updates on the current our method library. So I believe that we hope that Matt is enable data partners with small to medium-sized data to participate more odds network studies, like break this down. And I know this is a very difficult subject for all of us, so I'd like to repeat this in Korean. So, 네, 메티스 프로젝트에 대해서 잠깐 다시 한글로 설명드리도록 하겠습니다. 지금은 이제 우리가 그 어떤 사이트가 이제 연구를 시작할 때 그 내부적으로 연구를 진행을 해가지고 하고 코드를 이제 뿌리는 식으로 되어 있고, 이제 그 리절트를 나중에 다시 모으는 식으로 되어 있는데, 이게 지금 작은 일반적으로 이제 한 병원 정도의 작은 규모의 데이터에서는 이 시스템이 잘 작동하지가 않고 있습니다. 그래서 스몰 데이터를 갖고 있는 그 파트너에서는 이제 프로펜시티 모델 같은 게 제대로 피팅되지 않는 경우가 많고, 그다음에 아웃컴 모델에서는 노멀리티 업섬션을 만족시키지 못할 경우가 많습니다. 그래서 우리가 현재는 지금 해저드 레이쇼 1.02에다가 컨피던셜 인터벌 0.27에 3.78이다. 이런 것들만 이제 사실은 모아가지고 메타 애널리시스를 해서 이제 리절트를 보고 있는데, 그러지 말고 이제 우리가 이 풀 쉐입을 이제 어그리게이팅 하면은 훨씬 더 나은 이제 메타 애널리시스 리절트를 낼 수 있다라는 게 이제 마타인 닥터 마르타인 슈미가 이제 말한 내용이었고, 그래서 지금은 그냥 일반적인 그냥 메타 애널리시스를 하는 게 아니라 이제 쉐입을 모아가지고 메타 애널리시스를 하면은 조금 달라진다. 네, 그런 얘기입니다. 그래서 이전처럼 이렇게 숫자만 모으는 게 아니라 쉐입을 모으자. 그 리절트 모델에서 쉐입을 모으자. 이게 이제 닥터 슈미가 말해준 얘기고, 여기 제가 말한 거는 이제 그래서 이 부분 아웃컴 모델에 대한 걸 말해줬고, 프로펜시티 스코어 모델은 이제 큰 데이터베이스에서 프로펜시티 스코어 모델을 만들어서 작은 데이터베이스에 도입을 해보면 어떨까라는 생각을 했었고, 실제로 해봤을 때 조금 좋아지긴 하지만 크게 좋아지진 않습니다. 그래서 이게 결과인데 이제 이게 사실 0.1 밑으로 떨어져야 우리가 잘 됐다라고 말을 하는데 여전히 0.4 정도로 이렇게 큰 데이터베이스에서 작은 데이터베이스로 프로비티 스코어 매칭을 적용해도 그렇게 좋아지진 않고 있습니다. 그래서 다른 아이디어로는 이제 우리가 큰 데이터베이스에서 작은 데이터베이스로 한 번만 이렇게 딱 넘기고 끝낼 게 아니라 여기서 한 번 더 작은 데이터베이스 맞게 다시 업데이트를 하자. 그래서 이제 날리지 트랜스퍼 해가지고 다시 한번 거기서 임프루브를 시켜보자. 베이전 업데이트를 이용할 계획이고, 이렇게 되면은 꼭 우리가 큰 데이터베이스에서 프로비티 스코어 모델을 가져올 필요 없이 작은 데이터베이스끼리도 이 프로비티 스코어 모델을 공유하면서 서로 진화할 수 있지 않겠느냐라고 생각을 하고 있습니다. 그래서 이런 부분들을 이런 부분들에서 좀 작업을 하고 있습니다. 그래서 지금은 이제 병원 규모에서 이제 앞서 본 것 같은 레전드 하이퍼텐션 이런 스터디 같은 거를 좀 참여하기가 어려운데, 그렇게 되면은 이런 게 되면은 이제 좀 더 참여를 할 수 있게 되지 않을까 기대를 하고 있습니다. So I'd like again OHDSI Korea as a community. So Yuval Harari said that that scientific revolution was not the revolution of knowledge. It was the revolution of ignorance. We admit that we don't have the solutions to many questions. We don't know the answers. So we need to collaborate to answer most questions, like what is the best practice for hypertension and what is best practice for diabetes. It can actually save millions of lives in the world. And our mission is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions and better care. So this is our hope and our mission, and I hope you to join this journey too. Thank you for your attention.
Thank you, Dr. Yu. I think, although this is plenary session, so usually no Q&A, but whole session, most of today's session is plenary. So I think the quick 5 minutes Q&A is very adequate for us. So anyone who can ask questions, please introduce yourself and use microphone.
Hi, I'm Mi Young Park from Busan National University Hospital. My question is to Martijn. So, I really, it's a great talk and it's good guideline for our future research. But the thing is, I would like to ask some questions. Recently, I analyzed drug effects associated with diabetes from our CDM data. However, the results were different from the published papers. So we were a little bit confused. So I deeply agree with you that one-time analysis is not enough. So maybe we need more analysis with different approaches, like you mentioned today. But however, assume that if we analyze thoroughly, but still, if we have some inconsistencies with the previous studies in the literature, then how could we interpret the results, and how can we resolve the problem, and how can we justify the result based on CDM data analysis? And the other question is that
무선 마이크 없어요? 저 데스크에 마이크 좀 갖다 주세요. Please use the wireless mic.
You also mentioned about the validation. So what can be our ground rules for validating the results based on CDM data analysis?
Okay. Yep. Let me try and answer your questions. Thank you. As it comes to trying to reconcile new results with old results, there's always the possibility that there will be a disagreement between the two. So one of the important points about that I was trying to make is that in your own study you should have very strong diagnostics. So basically checking all the assumptions that you're making in your study. And if you believe that you have met all these assumptions, then maybe you should feel more strongly about your evidence compared to what is already known. But it's always a question of trying to synthesize our prior knowledge with new knowledge. We have our experience is that just one study usually is problematic in terms of interpretation, and I think that's one of the strengths of OHDSI, is that we can very easily have the study be replicated across a large number of sites, and that already gives much more confidence in our findings. So if we perform an OHDSI study where in 10 databases we observe the same effects, then that can already give us more confidence that maybe what we now find is true, and what was previously found was maybe if it was subject to some of the dangers that I pointed to, like publication bias or p-hacking or confounding.
Yes, so I was wondering that traditional methods by clinicians or clinical reviews, then they can willingly trust our data by observational studies. So can you, I mean?
Yeah, so I think as long as we adhere to the best practices and really make sure that we've checked all the boxes and reproduce our results over a great many sites, then it's going to be very hard to dismiss what we find.
All right.
Is my hope.
Okay, thank you.
Actually, I'd like to add one comment to Dr. Park. In your center, have you ever checked the discrepancy between clinical data warehouse and clinical data model? Because usually when we believe clinical data model totally, the conversion to CDM should be complete. But usually it is by a couple of or several students or maybe less experienced medical doctors usually. Maybe in usual centers. So there might be some discrepancies between real-world CDW data and CDM. So in those cases, after the analysis result might be different.
Yeah, even that RCT, right? Randomized clinical trials.
Yeah.
That data, when we compare it with RCT and the CDM results,
Okay.
it should be different. So which one can be the trustworthy compared to RCT results and CDM
Martin, I
results?
think this is not the which one is better. Do you like mother or father? Okay, so I think that that is kind of the policy and how to make CDM or those kind of considerations. What do you think about it?
Well, so to be clear, there is always a reason why there is a discrepancy. The question is, will we be able to find out? But briefly to your point, so one of the checks that needs to be performed is data quality. And so we need to be very certain that our conversion into the common data model actually does not introduce any further error. And so there's actually quite a lot going on in OHDSI currently as it comes to data quality that I did not have time to address.
All right.
But that is another very important part of we need to cover all our bases, is the expression, I think, to make sure that we've also ruled out that possibility, and that to make sure that we produce reliable evidence. But in the end, if there is a discrepancy between a randomized trial and what we find, then there must be a reason.
Yeah.
It's not always possible to find out which.
All right.
Thank you.
I would just like to,
Okay.
to comment
Yeah.
on your point there. around the world we hear concern about the idea of converting data from its original form into the common data model because of concern that the data will have information loss or be distorted in translation. And yet, time and time again, what we've learned is when we've identified data issues, it's actually data issues that exist in the source data, but we never had the ability to find them before. Mm-hmm. I think actually what using the common data model achieves is the ability to put transparency onto data and to identify where the data are useful and where the data are not trustworthy. There is a concern that achieving that transparency might represent an additional possibility of error, but our experience around the world thus far has actually been that the main thing we've identified is we've discovered data quality issues that have existed in all prior research done on the source data. It's just that no one ever had the ability to identify it before. So I think that the common data model translation, we do need to make sure that we are applying data quality standards, but we also need to recognize and appreciate the value of transparency. Okay. And that the value of finding issues in new ways that we couldn't have before.
Thank you.
Any other questions? The short questions to Martijn and Pat. Usually, for making clinical data model, we use the EHR and claim data. So, have you ever used the data from the manufacturer company or medical device company or other pharmaceutical company?
So the OMOP common data model was designed to support longitudinal patient level data of various sorts. Here we're talking a lot about insurance claims data and electronic health record data. But another valuable type of observational data are clinical registries, which are prospective studies collected observationally and oftentimes sponsored by large companies. Many of them have been converted to the OMOP common data model because in order to do research, one needs to have some data standard to apply methods. And it has been interesting to see within the OHDSI community that groups have come together, particularly for specific disease areas. Like in oncology, there are many different registries, or in rare diseases. And I think a community-based approach that can bring those small data sets together to answer questions across those data sets will have tremendous value as a community. And to learn across registries in combination with what we can learn from claims and electronic health record data.
Okay, thank you. Thank you. The time is up and we will close this session. Thank you.